Hello and welcome to another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 10, Lesson 9, Volumes of Right Prisms. This happens to be, at least at this point in time, our last lesson of Math 7. So congratulations if you're watching this video in sequential order. You made it, and you don't have to watch me again until Math 8. Or maybe never at all. Anyway, volume obviously is a very important property of three-dimensional solids, right? It measures the amount of space that is enclosed within a solid. Last year, you looked at how to calculate the volumes of right rectangular prisms, okay? But they were always rectangular, meaning their bases were rectangles, and then the lateral faces were perpendicular to the bases, and they were also rectangles. So let's review how to find the volume of a right rectangular prism in our first exercise. All right, here we go. Volume is a measurement of the three-dimensional space that lies inside of a solid. Now we typically do this measurement by counting the number of unit cubes that lie within the solid. And the easiest way to visualize that process is if we're looking at a right rectangular prism, a box. Let's take a look in exercise number 1. A right rectangular prism, box, is shown below. It has dimensions of 6 inches wide, 5 inches long, and 4 inches high. We want to think about how many cubic inches fit inside of this solid, shown at a different scale below the diagram. Letter A. A cubic inch is a cube that has an edge length of 1 inch. How many of these fit into the bottom layer of the solid? All right, so make no bones about it. What I'm counting is how many of these things fit inside of this. Now, keep in mind that this is drawn at a completely different scale, right? Each one of these kind of cubes that you see here is supposed to be one of these. And I just want to know, in this bottom layer of cubes, how many of those fit in. Pause the video now. This should be pretty easy. Well, we have a row of 6 that are here, and then we have 5 rows of them. Or we have a row of 5 here, and we have 6 rows of those 5. Either way, right, we've got 6 times 5, or 30 in that bottom layer. All right, now, this is extremely important for the rest of the lesson. Letter B. Your answer in A corresponds to what measurement of the base? In other words, if I take the base, which is a rectangle that measures 6 inches long and 5 inches wide, that 30 actually corresponds to something about the base. And what is it? Well, it happens to be the area of the base. Now again, that's absolutely critical to understand, right? If I drew that base out, I have to draw it kind of small like this, right? And it was 6 inches by 5 inches, right? The whole point is, you know, if I kind of 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, right? Right, I would have 30 unit squares that would fit inside of that base. And of course, on top of every one of those unit squares, I could put a unit cube. So imagine that base actually kind of being a grid, right? With 30 unit squares, and you'd take a cube and you'd put one on one of the squares. Take another cube and put it on another square. Another cube and put it on another square. And eventually you'd put 30 of those cubes down on the 30 square inches that sits in the base. Now, we're still trying to figure out how many cubes fill up the solid. Well, how many layers of cubes will it take to fill up the solid, and what does this correspond to? So how many layers of cubes would I have? That you can see directly from the picture. Go ahead and answer that question. Well, I'd have 4 layers, right? I mean, there they are. 1, 2, 3, 4. And that obviously just corresponds to the height. Right? So the height tells us how many layers of cubes we have, and the area of the base tells us how many cubes lie in a single layer. So there would be 4 layers, and that corresponds to the height. All right, so what's the volume of the solid? Well, the volume of any solid is how many unit cubes fit in. We know that we've got 30 cubes in a given layer. We know we've got 4 layers, and so ultimately we have 30 times 4, or 120 cubic inches. Or if you like it like this, 130 inches raised to that third power. All right, now what's extremely important is that you understand this idea of that area of the base, all right? Because the plain fact is, if we know the area of the base, then we know how many cubes fit in a layer. Then if we know the height of the figure, we know how many layers we have. So we can simply multiply the area of the base, that's 30, by the height, that's 4, to get how many cubes fit into our solid. 120 cubes fit into this solid. So let's summarize that with a formula. All right prisms have the same formula that can be used to calculate their volumes. All right prisms, not just ones that have rectangles as their bases, right? So the volume of a right prism is given by B times H, where B is the area of the base and H is the height of the prism. In the case of a rectangular prism, the area of the base is just length times width, and then you'd go on and multiply by height, right? Now here, I wanted to draw a prism, a right prism that wasn't rectangular. You know, this is a pentagonal prism because it's got a pentagon. But if I knew the area of that pentagon and I knew the height of the prism, then I could just find the area of that pentagon, multiply it by the height of the prism, and that would tell me the volume. Because ultimately, as long as I know how many squares lie in the base, then that's how many cubes lie along that base level, and then the height is how many of those levels I have. So let's take a look at an example of using that idea for a very, very small prism. Exercise number 2. A thin steel plate has a base that measures 56 centimeters by 48 centimeters and a constant thickness of 0.2 centimeters. What is its volume to the nearest cubic centimeter? All right, well again, it goes back to just this idea that the volume of any right rectangular prism is length times width times height. The length times the width gives me the area of the base, kind of shaded darker here. The height gives me how many of those stacks I can have. And I know that's a little bit weird because it's a decimal, but you could think about it as 2/10 of a stack, whatever. But at the end of the day, right, my volume is simply going to be 56 times 48, and that's really the area of the base, times, well, I won't put the times symbol there, times 0.2. which is the height. Now, of course, our calculator makes this one fairly easy. 56 times 48 times 0.2. You know, as long as I can hit the enter button. And my volume is 537.6, but I want it to the nearest cubic centimeter, so 538 cubic centimeters. Make sure not to tell me square centimeters or centimeters, right? I'm measuring how many unit cubes could fit in there. I might have to slice and dice those unit cubes up, but ultimately 538 unit cubes would fit inside of this solid. Well, 537.6. Okay, now let's work with some right prisms that aren't rectangular. As long as we have a prism whose cross sections parallel to the bases do not change, then we can find its volume simply as the base area times the height, right? So we have to kind of get away from that length times width times height regime for the next few problems. And let's see how that's done pretty easily with a triangular prism. Exercise number 3. A right triangular prism is shown below with the noted dimensions. Find its volume in cubic inches. Show your work. All right, this is really no different than what we've been doing, right? So the volume is the area of the base times the height. It just so happens in this case, the area of the base is the area of a triangle, right? Not the area of a rectangle. So in this case, I kind of like to find the area of that base first and then use that in this problem. So what do I have? I have a triangle that's a right triangle, right? I can see the right angle symbol there. So I have a right triangle. Here, I'll draw it kind of like this so you can just all see it, right? A right triangle that's 7 inches by 12 inches. that's my base, right? So I can find its area by simply doing 1/2 times 7 times 12. All right, I can put that in my calculator, or for me, I can just do this and get a 6, and that's going to be 42 square inches. And yeah, square inches, right? Because it's an area. It's not a length and it's not a volume yet, right? But now that I've got the area of my base, it doesn't matter what that base was. It doesn't matter whether it was a rectangle, a triangle, a pentagon, a hexagon, an octagon, a figure you don't know the name of. It just doesn't matter. Right now, I can say my volume is going to be 42 square inches times the height, which is 10 inches, and this is pretty easy, 420 cubic inches. By the way, notice how nicely all the units work out, right? Here I've got inches squared times inches, and that's inches cubed, or cubic inches. All right, anytime you multiply an inch times an inch, you get a square inch. Inch times inch times inch, you get a cubic inch, right? So we've got cubic inches. Now, let's look at one that's far more complicated. Okay, now in the real world, and this can be tricky for folks, in the real world, sometimes prisms do not lie on their bases. The word base almost implies that it should be at the bottom of the figure, right? Sometimes the bases are in fact vertical. Just realize that the height is the distance between the two identical bases. So let's look at kind of a classic case of that in exercise number 4. A storage shed is designed using a right rectangular prism topped with a right triangular prism as shown. Find the volume of the shed in cubic feet, show your work. Okay, great. So the idea is that the bases are actually this pentagon, right? And then an identical pentagon that's parallel to it on the back side of this storage shed. The height, right? The height of this thing is actually the 12 feet. It's not really a height, right? It's really the distance, the perpendicular distance between the two bases, all right? Think about the distance between the two bases of a trapezoid, right? Right? That's the kind of the same idea. All right, so we want to find the volume of the shed in cubic feet. The first thing I would suggest doing is find the combined area, find the total area of this front face, all right, and then just multiply that by that 12 feet. Pause the video now and see if you can come up with this volume. It's going to be fairly substantial. All right, well, let's come up with the B, if you will, right? The B, the area of the base, is going to be comprised of two things. One is going to be this rectangle, okay? And that rectangle is 16 feet wide and 6 feet tall, right? Let me label the 6 right here so you can see it a little bit better. It's listed right here, but that's the same dimension there. So that's going to be 6 times 16 plus, right? So that's that rectangle. Plus, now we'd like the area of that triangular portion. Now, what does that triangle look like, right? That triangle is 16 feet wide, and it's 2.5 feet tall. So that triangle has an area of 1/2 times 16 times 2.5, right? And that's my triangle. All I'm getting in this calculation is the area of the base. And again, just because it's not sitting on the base doesn't mean it's a base. The base is just two polygons that are identical and parallel. And that's the front side of the storage shed and the back side. Hard to point at it exactly. So let's figure out that area. Let's bring this thing up. We can put this entire thing in at once, or you could calculate the two separately if you'd like. It doesn't really matter. I'm going to do it all at once. So 6 times 16 is going to be the area of that rectangle. Plus, I'll do 0.5 for 1/2, right? We all know that 0.5 and 1/2 are the same thing, or at least I hope we do. And then times 2.5. If that's confusing, do it separately, divide it by 2, what have you. So that area is 116, and that is square feet, right? So there is simply the area of that front side of my storage shed. Now, if I want the volume of my storage shed, I simply need to multiply that area by the distance between those two identical bases. And that then is going to be 116 square feet times 12 feet. And that's going to be a volume of what? Now, I could have left that out there. Let me bring this up a little bit farther. 116 times 12, 1,392 cubic feet. All right. Nice big volume, which we want. We want that in a storage shed, right? The bigger the volume of the storage shed, the more we can put in it. All right, let's finish this thing off. We've got one more piece of this problem. Let me get the calculator out of the way so we can all see it. Let's take a look at letter B. What percentage of the total volume is taken up by the triangular portion at the top of the shed? Round to the nearest percent. Show how you found your answer. So maybe, I don't know, maybe for some reason we can't really use the space up here. Or maybe because heat rises, the space up here gets very warm and we only want to put stuff up there that isn't, subject to, I don't know, like heat damage or something like that. So we might want to know what percent of the total volume is taken up by that upper triangular portion. Well, we know the total volume. What you need now to do is figure out the volume of that portion only, and then figure out, right, what percent of the overall volume that takes up. Pause the video now and see if you can remember how to do some percent work. All right, well, let's figure out the volume of the upper portion. Now, in order to do that, I got to go back to just this area, right? So in this case, just for the top, the volume of the top portion, right? Well, again, we already kind of know what the area is, sort of, right? The area of the base now is only going to include the triangular portion, 1/2 times 16 times 2.5. Okay, and that's going to give me, here, this time I'll do it without using the 0.5. 16 times 2.5, and then we'll do divided by 2 instead of multiply by 0.5. Either way, we get a grand total of 20 square feet. Now, if I want to know the volume just of the top, I'm going to take that 20 square feet, right? I'm going to multiply it by that 12 feet, right? That 12 feet right there. Come on, come back down. 12 feet right there. And that's going to give me 240 cubic feet. Now, right, I still am not done with the problem. What I do know is that 240 cubic feet out of the 1,392 cubic feet lie in the triangular portion. So I need to know the percent. Now remember, whenever we want to take a fraction of a whole and change it into a percent, we're just going to take the part divided by the whole and then multiply that by 100. So if I take my 240 and I divide it by 1,392 and I multiply by 100, that will give me my percent. So what will I have? 240 divided by 1,392, right? You can probably just tell from the decimal itself, but multiplied by 100 makes it real easy to see. The percent is 17.24, etc. Round to the nearest percent. 17% is taken up by that upper portion, right? And that's a good thing to know, right? It's less than 20% that's being taken up. So even if we couldn't store anything in this upper area, we still know that more than 80% of the total volume is contained in that lower rectangular portion. All right, let's wrap this up. Now, so what did we really do today that was an extension from Math 6? Well, in Math 6, the only kind of volumes that you calculated were volumes of right rectangular prisms that are basically volume equals length times width times height. That's it, right? And we did mention in Math 6 that it's really the base area times the height, but then we just kept using length times width times height. Now the expectation is that you can come up with the volume of any right prism as long as you can come up with the areas of the bases. Now don't get me wrong, there's only a few things you can really find the area of. Those are squares, rectangles, parallelograms, triangles, and trapezoids, right? So we're not going to give you a pentagon as a base unless we tell you the area of that pentagon, and then you would just take that area, multiply it by the height, and you would get the volume. All right, well, I'd like to say you're going to use this in more lessons in this course, but quite frankly, this is the last lesson in Math 7, all right? And I just want to thank you for joining me for this course, NGen Math 7, and I want to wish you, as always, a good math class and good success in your future math courses. For now, I just want to say my name is Kirk Weiler, and as always, keep thinking and keep solving problems.